Welcome to Tollefson Physics. So today what we're going to do is we're going to draw another quantitative force diagram, but this time it's going to be for an object that's sitting on a hill. And what this is going to do is it's going to force us to change our coordinate system. But we're going to apply all of the same principles that we applied previously. And so the problem that we're going to look at is I put a car on a hill. All right, car on a hill, which is has a 15-degree angle with a horizontal. And the car, we'll say, is 1,000 kilograms, nice round number. And so what are we going to do? We're going to go ahead and we're going to draw a force diagram for that. And so let's draw the force diagram in purple. And so what do we have going on there? Here's my center of mass. I'm going to have a force due to gravity. And once again, I could calculate it if I want. So remember, force due to gravity is mass times the acceleration of Earth's gravity. And so 1,000 times 10 is 10,000 newtons. Okay, what about my other forces? So I like to kind of indicate where my hill is just so it's a little easier to draw, because the next thing I'm going to draw is the normal force. And normal means perpendicular. Perpendicular to what? To the ground. So that's why I drew the ground, just to kind of keep that in mind. And so I'm going to draw an arrow. It's a normal force because it's perpendicular to the ground. Right? And because I drew it that way, I guarantee you the normal force does not equal the gravitational force in this case. Now with just two arrows like this, you can see they kind of lean to the left, which means this object would accelerate to the left if I don't add another force. And so I'm going to add a force that kind of holds it on the hill. And that force is because of the tires against the pavement. And so that's going to be the force of friction. All right, so this is what my force diagram is going to look like. So now what I'm going to do is I want to analyze this. I actually can figure out what the frictional force and the normal force is because I know its mass, which allowed me to figure out its weight. And weight is a synonym for force due to gravity. But the thing is, these are not all orthogonal to each other. So I need to pick a coordinate system that will help me figure this out. And so the coordinate system, as I've mentioned before, I'm going to pick it along a direction that it potentially is probably going to move or accelerate. Like if the force of friction went away, it's going to go downhill. So I'm going to pick a coordinate system. I'll put it off to the side here that is perpendicular and parallel to the ground. So there's my xy in this case. And right, so because it potentially could accelerate this way down the hill. And what that does is my force of friction is already in the x direction, and my normal force, not well drawn, but it's already in the y direction. So those are fine. They're orthogonal to each other. So when I think about up equals down, right equals left, I'm going to think about it in these directions. So you can almost think about it turning it this way, if that helps you. And so I'm going to leave it angled like this. And so now I got to think about what's going on here. So this is not on the x, it's not in the x or y direction. So I'm going to make it in those directions. And the way that I typically do this, and you'll see in a minute why I do it this way, is I'm going to draw my arrow in the y direction. So I'm going to call this FG of y. Okay. So that's in the y direction. And then x direction is parallel to the ground. So I tried to stop my arrow in time for me to go in the x direction. So FG in the x direction. Oops, comma x. Yeah, I'll do it that way. So comma x. Those two arrows replace this that I smudged out, the 10,000 newtons. All right. So now I can go ahead and figure out what's going on. So I typically figure it out using this angle, and we'll see why in a moment. But this is going to end up being a force due to gravity. This is adjacent. And so adjacent and hypotenuse, because I know the hypotenuse is related to the cosine. And then this one is opposite that angle, so that is the sine of that angle. So what is that angle? Well, that angle we can figure out by looking at my dotted line here. So let me get this dotted line, and technically that's parallel to the ground, and this is 15 degrees according to the problem. So if that's 15 degrees, and this is a right triangle, this up here must be 75 degrees. and then I have another right angle, and so then that theta is the 15 degrees. And that happens every single time if you draw it that way. So you just, once again, got to remember your geometry. Got to remember that geometry. So what I'm going to have to do here is I'm going to have to take FG times the cosine of 15 degrees. So let's go ahead and do that. 10,000 times cosine 15 degrees. And that gives me a number that I'm going to, we'll round it to the nearest whole number. So that's 9,659. And in the other one, so we're going to do 10,000 again, times sine 15 degrees. And this is, write it here, 2,588 newtons. All right. So looking at this diagram from before, we know the down arrow equals the up arrow because I only have one up, one down, and the right arrow equals the left arrow. So I actually, from this calculation, since there's no additional forces, I know what the normal force is and I know what the force of friction is because up equals down, right equals left. So if we look at in the y direction, this is going to be, and I can write it out explicitly, right? Normal force equals force due to gravity in the y direction. And in this case, that number is 9,659. And then I can also, I'm going to write it on top of this, my right arrow, force of friction, equals my left arrow, which is force of gravity in the x direction. And so what did I find that to be? I found that to be 2,588. And there you go. So the difference in a problem like this one is that I needed to change my coordinate system to match the hill, because that's the direction it might actually accelerate in. And so that allows me to solve this. And this becomes really important for when this does accelerate, you're going to use the exact same ideas to solve this as long as your coordinate system is in the direction of the motion. All right, so hopefully these examples help you apply this to other problems.